So let's just go ahead and talk just a little bit more about hydrogen. And we tend to use hydrogen because it's the easiest possible element. If you think about hydrogen, hydrogen is going to have one proton, no neutrons, and then one electron that lives inside of these orbits or these shells. And that's going to make it more orderly than the other elements. And something that we can kind of see is the lines of hydrogen are actually going to get closer and closer and closer and closer. And what this means is these orbits are going to get closer and closer and closer and closer. You can kind of see this if we were to look at this energy level diagram for hydrogen. Right over there, that's going to be our ground state. The next shell is going to be really far away. We would call the shell n is equal to 2. And then n is equal to 3 is not such a big jump. To going to 4 is closer still, closer still, closer still. So the energy levels are going to get closer, and the lines are going to get closer, and eventually they'll merge. Now, if we were to look at hydrogen, then we would say here's the center of the atom, and the electron can live here. This would be n is equal to 1. It could live here, or here, or here, or here. Something that's kind of interesting is if we were to go ahead and talk about these colors or these lines, we know that this energy difference is going to be relatively large, and so we're going to get violet light. We're going to have a high frequency because we have a high energy. If we were to talk about this jump right here, it's less energy, so a smaller frequency, even less energy still, even lower frequency. So red, blue, violet, thinking back to Roy G. Biv. Now, this fellow by the name of Johannes Rydberg kind of discovered something. What he discovered was the sum of the frequencies of these two lines are going to equal the third frequency. So think about this violet right over there, that's going to have some frequency. And what he kind of discovered is if I were to have this red and this blue-green, and then if I were to have another one right here, if I added up these three frequencies, I would actually get the same frequency as the violet. Now that kind of makes sense because the energy is going to be equal to Planck's constant multiplied by frequency, and the energy of this violet should add up to the energy of this jump plus this jump plus this jump. These guys all add up, so these guys are all going to add up. Now, we actually have a special name for this. A fellow by the name of Ritz did some work as well. So it's actually called the Ritz-Rydberg combination principle. And all this really says is if we had some frequency from this jump right over here, and we had some frequency from this jump and some frequency from this jump, it would make sense that the energies are going to add up. Therefore, the frequency of C should be the sum of the frequency of A plus the frequency of B. So we can add all of these guys up. Now, the funny thing is back then they knew that this happened, but they didn't exactly know why this happened. Let me kind of change gears a little bit and talk about solids. When we talk about a solid body, it's not going to put off just one frequency. You can kind of think of this as ringing a bell. Suppose I had a perfect bell and I were to ring this bell, it's going to put off one frequency and one frequency only. This is a lot more like having a gas. But solid bodies are connected to one another. So think about more than one bell connected to each one, or connected to other bells by rods. And what we could actually say is it's not going to put off one frequency, it's going to put off a bunch of frequencies, kind of an average frequency. And the frequency is actually going to depend on the temperature or how hot it is. If we were to look at the light that comes off of a solid, it's not going to be a single color, but a smear of colors because of those connections. Interesting thing, as temperature goes up, the frequency is going to go up, and the smear is actually going to get wider. So here we have the brightness of light right over here. Here we have frequency, and that's also a fancy way of saying energy. We know energy is related to temperature. And if we could even say, Roy G. Biv, going up in the language of frequency. Here we have 1,000 degrees, here we have 1,500 degrees. We're increasing our frequency and also making this smear a little bit wider. And we could say that if something is hot, maybe you know that it's hot. Maybe you can feel it, but you can't see it. Maybe it's putting off in the infrared. You make it hotter still, you're going to get glowing red hot. You make it hotter and hotter and hotter and hotter, you're actually going to get something that is white hot. White hot is going to have all of these frequencies kind of smeared together. Now, what's going on here? We have a special name for this. We call it incandescence. Essentially what we're doing is we're talking about solid objects, not gases. If we were to think about ringing an individual bell, we're going to hear a distinct frequency. This is kind of like a gas. But if we took a bunch of bells and chucked them all together in a box and we were to shake that box, then we're going to hear a whole bunch of different frequencies because there's some connections going on here. The same is true for the colors of light that come off of a gas versus the colors of light that come off of a solid. These guys are all jumbled together. These guys are not. Now, I do want to talk a little bit about absorption spectra, and something that I said is if we had hydrogen, we're going to have some ground state, and then we're going to have some excited state, and then we're going to have some state above that, and then some state above that, and so on and so forth. And I said that we're going to get certain colors, certain frequencies, as electrons make this jump from high ones down to low ones. However, we could also say that hydrogen is preferentially going to absorb those wavelengths, and those wavelengths only. This would be the absorption spectra, this would be the emission spectra, and as I said earlier, these guys are going to line up one for one. Now, what's up with that? Well, if I try to excite hydrogen, then only certain frequencies are going to allow the electrons to make that jump, or the next jump. And they're going to correspond to the same exact energies, the same exact frequencies as what comes out of this hydrogen when electrons jump down. So it kind of makes sense that it's going to take this energy and this energy and this energy. An energy that would pop it up to right here, well, that's not good. And the reason for that is because there's not a shell there for the electron to live at, so it's not going to absorb that one. Now, something that's kind of interesting is this idea of fluorescence. And it turns out that many materials are excited by ultraviolet light. Why is that? Well, ultraviolet light has a very high frequency, therefore it has lots of energy. And what it can do is it could take an electron, and it could pop that electron from the ground state up to any one of these states up here, say a really, really, really high state. Now, if that electron were to jump down, it doesn't have to jump down to the ground state. So here we're going to have a high frequency. Here we could have a lower frequency, and maybe it's even in the visible. So ultraviolet light is really good at exciting something, but then maybe it's going to de-excite in the visible. And this is why when you put crayons or something into a black light, you can see all sorts of cool, funny colors coming off of it, because what we're seeing this right here. Now, really quickly, this is kind of a better graphical representation of that. Here we have some ultraviolet light coming in, and we've taken an electron from our ground state, and we've kind of popped it up to this really high state. Again, high frequency, high energy, and when this guy jumps down, it doesn't have to jump down to the ground state. It could jump down to this one, or it could jump down to this one, or it could go back to the ground state. If it went back to the ground state, it would emit some ultraviolet. But if it emitted this one, for this particular jump, it's showing this guy right here to be green. If it did this one, maybe it would be blue. If it did this jump right here a little bit later, maybe it would be red. So many substances can get excited, go to a really high state, and then slowly work their way down the ladder, or down the steps, if you will. Now, you can kind of think of this just looking at some steps, and these steps would be the energy levels. This would be n is equal to 1, n is equal to 2, 3, and 4. And when the electrons make these jumps, then they can jump to any step they want. They can't jump between the steps, but they could jump from 4 to 3, and then 3 to 2, and then 2 to 1. And maybe it took some ultraviolet to get these guys up to 4. But this guy right here might emit some blue, this guy right here might emit some green, and maybe some cyan. If we were to jump directly from 4 to 2, that's a big energy jump, and that's going to be a high frequency. And you can see that this one right here is wiggling up and down very rapidly, this one less so. So this guy right here might be closer to violet than to blue. So I might say that this one right here is blue, that one's violet. Bear in mind, at the end of the day, the sum of these frequencies are all going to add up, just like the sum of the energies should. So this one plus this one should be equal to this one plus this one plus this one, using that Ritz-Rydberg combination formula. Now, kind of a real-life application of fluorescence would be a fluorescent lamp, or a CFC. And these guys right here are pretty straightforward. We're going to have a light bulb, and this light bulb, or fluorescent light I should say, is able to excite electrons using some high voltage. There's some transformers going on in here, and you can see some high voltage bombarding some stuff inside of this tube with energetic electrons. In this case, the energetic stuff is mercury, and you're supposed to dispose of these things properly. There's a reason for it. It's because there's mercury in them, and mercury is not good for the brain. And what's going to happen is these electrons are going to excite the mercury, and the mercury is actually going to spit off an ultraviolet photon. Now, we can't see the ultraviolet photon, but what happens is these things are coated with phosphor. And if you ever break these things open, they have this really fine dust that comes out, and that's essentially what you're looking at. And it's going to excite that phosphor, and the phosphor is going to emit all the colors of the wavelength, and so it's going to emit white light. One thing to bear in mind is this process doesn't have a limit. We can excite this mercury infinitely until the end of all days. The electrons will jump up, they'll come back down, and it doesn't wear the mercury out. What wears out is going to be either the transformer or this guy right over here. Now, something that's kind of interesting is it doesn't always happen instantaneously. When we talk about fluorescence, we are talking about something that happens instantaneously. This is going to be a relatively quick process. However, if we were to say, what happens if the electron becomes stuck in one of those higher order energy states? What happens if it takes seconds or minutes or even hours for the electron to hop back down? Pretty straightforward. We actually are going to call this guy phosphorescence, and this process is essentially the same process, only it's just a little bit slower. For example, if we were to look in the ocean, there are large organic molecules that can essentially become stuck. So there's a time delay between exciting this thing and the electron hopping back down, between the de-excitation, and we can get something that's very beautiful, like these guys right here. These guys right here absorbed energy when the sun was up, and then it just takes a little bit of time for the energy to come out, and it does come out as visible light. Now, of course, we do have names for these things. What we're essentially saying is we've gone ahead and we've excited some molecule with some visible light. We've given it some energy, and it doesn't de-excite immediately. It's going to enter what we would call a metastable state, and stable means it just takes a long time. And it could be minutes, could be seconds, or it could be several hours. And what's going to happen is eventually it's going to emit some light, but maybe it's going to take a little bit of time because it's living in this somewhat stable state. When the lights go out, we can still emit these photons. Special name for this would be called bioluminescence, and some things like jellyfish, like you saw in the last slide, they can hold on to this energy for quite a long time.